I will tell you in your 5 minutes.
Okay, I will just put up a counter. Okay, I hope you can hear me well. So today I want to talk to you about integrating 19F NMR focus screening with make-on-demand chemical spaces for enhanced fragment follow-up. And if I can switch the slides, there we go. So 19F NMR screening has been a core part of fragment-based drug design in Novartis for quite a while now. We really try to do these fragment-based approaches as alternatives to the classical high-throughput screening sort of ways to find hits. And what we try to achieve with this is to get maybe higher hit rates, lower molecular weight hits, so we have a little bit more flexibility to expand molecules, and generally hits with higher solubility. But this usually comes at the cost of a lower affinity starting point. And so what you see on the right on the slide, on the top right, is the lead fragment found for vemurafenib. Vemurafenib was the first drug approved, made by, or developed by fragment-based methodology. And you can see by the affinity annotated next to that lead fragment that it's over 200 micromolar. That is, first of all, it's a censored value. We don't even know the exact value, and we know that it's a pretty high value. And this is a little bit difficult to convince your chemistry project of to follow up on, because if they have maybe a greasy but large, greasy and large HTS hit that is measurable by their primary assay, then chances are they will want to maybe follow up with that rather than the unmeasurable fragment, which is a little bit more risky but may have more potential. And so we do a lot of this through 19F NMR screening. We had an introduction of NMR-based screening yesterday by Thomas's talk, so I won't go too deep into that, but this is how our spectra look like on the left here. So you have this, yeah, I hope you can see the, yeah, then we will go with just the cursor. So here at the top is a mixture spectrum of a bunch of compounds in a mixture that we put through 19F NMR. The 19F, which is the most abundant fluorine isotope, is the atom giving us the NMR signal. And each one of the peaks that you see in the spectrum roughly corresponds to one compound. And we have one pointed out here. This compound with the CF3 group up here, all of the fluorines in that CF3 will give the same sort of signal, and that's why it's only one signal. And the signal we look for when we do a screening format of this is that we have our compound spectrum, and then we add protein. This is this spectrum here, and we see that the peak has disappeared in this case, and this is what denotes the binding process. This can be a disappearance of the peak, but it can also be just a significant reduction of the peak. The last process that we do in this screening is that we add a competitor. We add a known binder to a known binding site and see if the peak reappears. Because if the peak of that particular compound reappears, we know which binding site it bound to because it was just pushed out of that by the competitor. So this has a little bit of the overview of the screening process. One of the most important things to know in this context is where the peaks appear so that we can really assign those back to the compounds. So we have a static fluorine library for this, the LEF 5500, and it tries to do what most fragment-based libraries do, that is cover as much of the chemical space as possible. And this is a little bit of a demonstration of how we try to do that in the expansion of the LEF 4000 to the 5500 compounds it is now. However, despite our best attempts, we do often find that it might be useful to do a focus screening for a particular target of particular molecules. And so we also established a focus screening, the 19Focused screening methodology, where we can take compounds from various sources, generate a fluorinated set of molecules, and then generate ad hoc mixtures that we screen in 19F NMR. And what I've pointed out in these blue circles in this workflow is left shift. Left shift is a prediction method for the chemical shift of the compounds, that is where they appear in the spectrum, a very important part for us to then, to first of all generate the mixtures, but then also to deconvolute which compounds actually hit. And this was, up until now, largely an ML workflow. At the moment, it's an XGBoost with molecular fingerprints. But we've also extended it with a QM arm now, and the QM arm is there to deal with a lot of novel chemistry. The ML does have issues sometimes when it encounters chemistry it's never seen before, and then we found that the QM processing is a little more robust. I'll talk a little bit about that later as well. So we want to do this in make-on-demand spaces, and we're doing this in the most prominent one of them, the enamine real space, which we've heard by Anna yesterday introduced. My numbers show that it's 76.9 billion at the moment. This is a slide I have to update every time I present it. And these over 70 billion molecules are generated from a number of well-validated parallel synthesis protocols and the building blocks to go along with them. And this success rate of 80% is really what makes these molecules not just virtual molecules, but readily accessible molecules, which is what the REAL acronym stands for. So we want to work with the enamine real space, and we wanted to do it in a few different ways. I will go into the 3 different approaches in a moment. We selected fragments through 3 different approaches, generated ad hoc mixtures from those, actually performed the 19F NMR screening, and then we wanted to follow up on them in the real space again, which we'll be doing with chemical space docking, followed by one last step of FEP prioritization to really decide which molecules we were going to buy. So the 3 conceptual approaches that we wanted to do were, on one hand, close analogs. We wanted to go into the enamine real space, do precise SAR, do this through maximum common substructure searches, and find things that were similar to known chemistry. Then we wanted to do some distant analogs. We wanted to use a method with scaffold hopping potential, in this case fast rocks, which was supposed to look for structurally more different matter, still biased a little bit by known chemistry, but really focusing on novelty. And then in the last approach, we wanted to start with the actual building blocks, encoding the enamine real space. Conceptually, if you take a building block from that space, you are guaranteed follow-up, because that building block will be involved in a number of reactions, which you can use to follow up on molecules you found, or the building block you found. So I won't actually be showing any compound or target information in this presentation. We're still fighting for that in legal, so you will have to wait for the paper on that. I will show you some numbers. So in the close analog set, which was quite a manual thing of repeatedly doing maximum common substructure searches, we have around 80 molecules, then around 1,300 through the fast rocks approach over an enumerated set of the enamine real space. And then in the building blocks, we effectively filtered down to those that had fluorine, that had particular properties, and trying to avoid things like covalency, which are very quick to mess up your screening. So we collected a number of fragment-like molecules and went into further in silico characterization by simple properties, by somewhat more complex properties, throwing everything at our target in a docking once, and lastly doing a visual inspection of all of this to arrive at 125 molecules that were actually deliverable, 30 close analogs, around 30 distant analogs, and then a little over 60 building blocks. We thought that it was not a bad idea to have a few more building blocks than the others, just because these were definitely the most riskiest set. They had not been biased by any kind of known chemistry, so we had no idea how well these would bind. We did a pre-screening. We did a pre-screening by SPR and DSF just to see what kind of hits we already had in the set. We found 9 hits under 100 micromolar in the SPR, 4 in the close analogs, 4 in the distant analogs, and 1 building block, which was very encouraging. But these were too easy for us. So in a normal project, you would get 9 hits. You would see, we got 9 hits from 125 molecules. This could be something that we can start with. But we wanted to go for challenging hits. And so we took those 9 out of the set and performed the screening by 19F NMR. So I want to talk about a few specific parts of this screening process, starting with the QM predictions that we did to do the chemical shift prediction. So we added QM prediction to left shift to handle compounds far outside our training set. QM is a causal method more than ML, which is very limited by its training set. And if you go too far outside of that, the ML method does go a bit crazy at times. QM is not necessarily the magic bullet for precision. When you have something well covered, when you are working in a place in the chemical space that's well covered by your ML training set, then you do often have higher precision with the ML than with the QM. But QM was really good for these compounds outside of the training set. However, QM is a bit of a different method than I think a lot of us are used to working with, and you have to be fairly precise with your handling there. So on the top right, you see trifluoroacetate. a molecule that I'm doing a prediction for here with its 3 fluorines. The 3 fluorines will be equivalent and are expected to rotate in solution. And what we do to, well, when you give that to your QM engine, you give it 1 conformation and you still get 3 different numbers out for the 3 different fluorines, and we average that then to simulate this rotation. In the table under that, you see the actual values that we predicted here, the shieldings, not necessarily the shifts, but the shieldings are linearly interconvertible to the shifts. And the 2 different columns in the table are once one where at some point in this pipeline, which is of course implemented in the RD kit, I wrote this to V2000 moles. And on the other hand, in the other column, those with full coordinates coming out of the QM engine, so 8 decimal places versus 4 decimal places. And this does actually have an effect on the prediction. It's a 0.02 ppm effect, so it's a fairly small number, but this is still 10-fold higher than the experimental precision. And I know that if I had to go to an experimentalist and tell them I introduced a 10-fold higher than experimental precision error because I'm a bad programmer, then that would be very embarrassing for me. So there are some growing pains dealing with QM pipelines in various software, and this is not just an RDKit thing. This is definitely not just an RDKit thing or a file format thing. This is also enough in vendor software. One more thing I will do is mixture design. So mixture design for these kinds of mixture screenings can be an interesting algorithmic challenge. On the right here, you see some people doing this for a proton NMR. In proton NMR, you have a lot more protons in molecules than you have fluorines. And so you have a lot more potential for overlap, for the peaks to overlap, as you can see here. And what you're optimizing is at as little overlap as possible so that all the peaks are still very assignable. Now, this is a little bit easier for us in 19F NMR. And when I approached this problem, I thought, okay, this is a simulated annealing approach. I probably wasn't going to need a simulated annealing. I thought I would do a random baseline, and then I would do a greedy algorithm, and then I would do a branch and bound. And then I was horribly outperformed by a chemist in an Excel sheet. So it's worth to sometimes talk to your chemists. They were probably doing this before you, and they probably have an idea how to do this. And the method just works by sorting everything by chemical shift, and then periodically assigning the first compound to the first mixture, the second compound to the second mixture, which wonderfully optimizes the distance between all of these peaks. And is also, because it's literally in an Excel sheet, a very flexible approach, and you can do things like separate compounds with uncertain predictions into different mixtures, very manually, very visually. You can avoid other sorts of risks. So if you have solubility risks for some of the compounds, you don't know if they're actually going to be soluble. This is a peak disappearing in your spectrum, which is very, very uncomfortable to then assign. And so it's very nice to only have 1 peak disappear in your spectrum, because then you can assign it by exclusion. So this is a little bit the mixture design part. To give you a little bit of an overview of how the prediction itself performed, we performed better than in the validation that we did for our chemical shift prediction workflow, which is always very gratifying if you're harder on yourself in your validation than in the prospective case. We usually separate the performance metrics by fluorine motifs, and I'll point out the CF, which has the most error here. It also has the most variance, so it goes across the largest range of the spectrum. So numerically, it just has the most error possible. However, here in the red circle, I've circled a few compounds that were very difficult to handle on both an ML and a QM level for reasons such as we didn't have the stereochemistry, and so we really couldn't do QM on some of these. And just generally, even if we could do QM, the errors were pretty high. So you will, in these sorts of dynamic situations where you keep seeing new chemistry, keep hitting cases that you can't handle. And so we hope that with the addition of QM, we can at least handle some of them better. These could all be assigned by exclusion, luckily, but yeah. So the follow-up we did was in chemical space docking, and this is the Biosolve IT's chemical space docking, who actually deliver this as a software tool. And they do a synthon-based combinatorial docking approach, an incremental growing approach. So the question was, now that we have hits coming from these different sets, we need synthons to anchor into our pocket to then grow from, to combinatorially dock from. This was very easy for the building blocks. The building blocks we could just convert into the synthons it corresponds to. The other sets, for example, molecules coming out of the distant analog set, you would then have to partition once again into the synthons and then take one of the synthons to actually anchor in the pocket. which means you have to refine it. And gratifyingly, we did refine that. And that is a little bit what I'm showing in this heavily, heavily censored molecule at the bottom right here. So one of the distant analog compounds was coupled over an amide. And you could really find both synthons making up this compound through the chemical space docking in 3D, in an exact search, not an overnight, but an over the weekend calculation. And so I believe we do have the technology to do these sorts of exact searches in chemical spaces without necessarily taking statistical or other kinds of shortcuts. We did a fairly simple filtering cascade, which I won't go into for time. The one thing I will show is a little bit about the FEP prioritization in the end. So here are some actual results. So compound 1 was the one that we found, was a distant analog set compound that we found in the 19F NMR screening, which was above 100 micromolar in the SPR assay, which we managed to measure in a 19F NMR KI. You can also use 19F to do KIs. Measured at 870 micromolar. So it's an almost millimolar compound that we managed to optimize to compounds 2 and 3, which compound 2 is around 100 micromolar in the SPR. This was a little bit at the detection limit, so it's a bit, and that's probably where the difference to the NMR KI comes from. And compound 3, which is a clearly double-digit micromolar compound with 53 in the SPR and 66 in the NMR KI. So we did manage to go from a challenging hit at almost millimolar to double-digit micromolar, which is something you can maybe start a chemistry project on. Compounds 4, 2, 6 are there to show you a little bit the difference between how well the single-edge FEP translates to the affinities and cycloclosure FEP. Some of the issues that you saw with these compounds 4 to 6, which were very optimistically predicted at times, could be solved by cycloclosure FEP. Some could not. In general, single-edge FEP did the job that we needed it to do. And for these higher affinity compounds, it was actually quite okay. But yeah, so there's still disadvantages. There's advantages and disadvantages to this. So in summary, we tried a few different approaches to make on-demand spaces. We tried close analogs, which quickly gave us active hits, if somewhat boring. Distant analogs, which were also still influenced by known chemistry and also gave us hits, but we managed to explore a little bit more, and this was our most successful approach. And building blocks, which were the riskiest and which we had some issues with in the end. But conceptually still, I think it's the most interesting approach, even if it wasn't super successful. QM was an important addition to our workflow to deal with novel chemistry, but is a high precision method that you have to really be careful about what you're doing with all the floats that you're getting out of it. And then lastly, positioning the screening in a make-on-demand chemical space to then facilitate follow-up did really work for us, to go from a challenging hit of an almost millimolar hit to a double-digit micromolar. And so we think, or we hope that we can lower the hurdle to doing these kinds of follow-ups for challenging fragment hits in the future. So thank you for your attention, and shall we do questions?
Any questions about that? So if I understand correctly, you need a reporter ligand, the fluorinato, in order to do competition assays, right?
So yes, the question was whether we need a reporter ligand with a fluorine to do, and that's a little bit my question, the screening part or the KI part, or which part? The screening. So we don't necessarily need a competitor compound with a fluorine to do the screening. Our fragments are all fluorinated, so that's the signal that we're looking at. Yes, all the. So it can, of course, affect the binding. Fluorine in itself is an interesting motif to interact with the protein.
Explore chemical space at the very beginning when you want to screen as diverse scaffolds as possible.
So yes, the question was whether it is a limiting step that we need a fluorine at the hit finding step to find potential scaffolds. I mean, fundamentally, yes. I mean, it is literally a filter that we have to apply. I think it's a filter that we don't feel too bad about applying because we'd still find a lot of molecules, and a lot of molecules in drug design are fluorinated. So if I do this in numbers, there are around 200,000 building blocks in the version of the enamine real space that we got, and a quarter of those were fluorinated. So we reduced that significantly to the 6,000. Yeah.
I think half an hour to debate.
Exactly. You guys can talk
Yes.
about this over lunch. And there are other questions, if not, I have one. So I'm curious, the story about the digits and the
Yes.
computational chemistry workflow is interesting,
Mhm.
but how many other sources of error do you have in that prediction?
Yes, of course, this is
So
this.
conference-
Yes. Yeah.
You probably have implicit solvent,
Yes, unfortunately.
and those probably all are worse than 0.00.
Absolutely. So the question was, what other sources of errors do we have in our QM prediction, and may they overshadow the 0.02 error that we're incurring through floating point errors? Yes, of course, every kind of statistical error, every kind of, so implicit solvent definitely has a higher error than cutting floating points numbers. The thing is, this is a very simple technical thing that we can solve, whereas everything else is significantly more difficult and more scientific. I've always thought that the technology is the easier part and the science should be the hard, or is the harder part. And therefore, if you can solve technological error, then you really, there's really should be nothing stopping you.
It just may be that your bad numbers are more precise than they were before, but anyway, that's another discussion.
Yeah.
We have time for one more if there's anything out there. Okay, so Martin.